Today, we're going to get into something that is, quite literally, the foundation of all science. It's how we date ancient artifacts. It's how your phone gets you around town. We're talking about the art and science of measurement. So, how does it all really work? Let's dive in. Okay, just look at this for a second. These are incredible drawings from the Neux cave in France. And scientists, well, they tell us these are about 17,000 years old. How in the world can they know that? And for that matter, how does your phone know your exact location at this very moment? It all boils down to one single, powerful idea. And that idea is measurement. You know, it's the tool that we use to take something that's a total mystery and turn it into something we can actually understand, something we can put a number on. At its heart, measurement is actually a really simple idea. It's just comparing something you don't know to a standard that you do know. So when you weigh something, you're just comparing its mass to the standard of a gram. It's the same thing with length and the meter. It's really a universal language. And this is exactly why it's so incredibly powerful. It takes a vague idea, like, I'm feeling okay, and it makes it concrete. Your blood pressure isn't just good, it's 110/60. And that very specific number gives a doctor information they can actually act on. Measurement brings clarity. But, just writing down a number isn't enough. We have to be sure we're actually hitting the bullseye, which brings us to a really crucial idea. So, how do we know if a measurement is any good? How can we be sure we can trust the numbers we're getting? Well, it turns out there are two really important qualities that every good measurement has to have. And those are precision and accuracy. The best way to think about it is like archery. Precision is all about consistency. It's how close your arrows are to each other. Even if they're all in the wrong spot, if they're tightly clustered, that's high precision. Now, accuracy, that's about correctness. That's how close you are to the bullseye. So you see, you can be super precise but completely inaccurate. The real goal, of course, is to be both. Let's look at a real-world example. Say we have 3 students, and they're all asked to measure the exact same spring. They come back with these 3 different results. At first glance, they seem all over the place, right? So who did the best job here? Well, let's break it down. Look at student 3. They have the smallest range. That little plus or minus is only 0.1 centimeters. That means their measurement was the most precise. It's the tightest group of arrows. But, and this is the important part, if we happen to know the true length of the spring is 14.8 centimeters, then student 2 was actually the most accurate. They're the one who hit the bullseye. Now, you probably noticed that little plus-minus symbol. That's not a scientist admitting they made a mistake. Actually, it's a critical part of being honest in science. That symbol stands for uncertainty. And look, in science, uncertainty is not a bad word. It's an admission that no measurement is ever absolutely perfect. It tells you the range where the true value most likely is. So a smaller uncertainty, well, that just means you have a more precise measurement. And this gives us a golden rule for comparing different results. Scientists say 2 measurements are in agreement if their uncertainty ranges overlap. That's it. Even if the main numbers are different, if those ranges cross over, the results are considered consistent. Okay, let's go back to the cave paintings for an amazing example of this. This time we're at the Chauvet Cave. A team does a radiocarbon dating test and gets their first result. 30,940 years, give or take about 610 years. But of course, they don't just stop there. They take another sample from the same spot, and this time, the measurement is a little different. 30,790 years, with a pretty similar uncertainty of plus or minus 600 years. Then, a totally different team comes in later and does their own independent test. Their result is different again, 30,230 years plus or minus 530. So now we've got 3 different numbers. Is the science all wrong? No, not at all. They're actually in perfect agreement. And this is such a brilliant illustration of the idea. Even though the main numbers are hundreds of years apart, when you look at their uncertainty ranges, they all overlap with each other. This is what tells scientists their results are reliable. This is literally how scientific consensus gets built. So, how do scientists manage to get such good, reliable results in the first place? Well, it's not magic. It really just comes down to a few fundamental techniques of the trade. There are 2 absolutely essential keys to good measurement. First up, you have to calibrate your instrument. This usually means checking 2 things. First, that it reads 0 when it's supposed to,
And second, that it gives the right reading for a known, trusted standard. The second key is you have to avoid something called parallax error.
Okay, what's parallax? It's basically an optical illusion. You've definitely seen it. Hold up your thumb and close one eye, then switch eyes. See how your thumb seems to jump? That's parallax. The same thing happens if you try to read a speedometer or a ruler from an angle instead of straight on. The reading will be off. To get an accurate reading, you have to look at it head on, every single time.
All right, so now let's see how all of these ideas, precision, accuracy, all of it, come together in a piece of technology that I bet is in your pocket right now. I'm talking, of course, about the Global Positioning System, GPS. Your phone acts as a receiver, and it's constantly listening for signals from at least 4 of the 24 satellites zipping around the Earth. Now, each one of those satellites has a mind-blowingly accurate atomic clock on board. By comparing the time it takes for signals to arrive from different satellites, your phone can pinpoint your exact location. And this is where it gets really cool. The GPS in your car, it's precise to within a few meters, which is plenty good for finding the nearest coffee shop. But the high-precision GPS units that geologists use, they can measure the slow crawl of the Earth's crust down to a few millimeters. That's how we can literally watch continents drift. It's the same basic technology, just with wildly different levels of precision for different jobs. So, we've gone from ancient caves to satellites orbiting the Earth. What's the big idea here? What's the one thing you should take away from all of this? The big takeaway is that measurement is the invisible engine that runs our entire modern world. It's the language we all agree on to build everything from bridges to microchips. It turns the unknown into the known. So the next time your phone tells you exactly where you are, just take a second to think about the incredible, tiny, and precise measurements that are making that simple fact possible.